Okay, good afternoon everyone, or at least it's afternoon when I'm recording this. I don't know what it is where you are. Hold on, someone's talking to me. Gee, cracky. Anyway, today I want to talk about a problem-solving method that is not used often enough, in my opinion, by a lot of students. So you would no doubt be aware of all sorts of problem-solving techniques like use a table to list known cases and the solutions and see if you can spot a pattern and all these other things. This one's a little bit different, and I really want to cough. Let's see if we can put that off. I will, of course, start at the top of my document, and I will take a sip of my coffee. Okay, so this often happens when we just don't know how to start a problem. And the idea is that you give names or symbols to some of the quantities in your problem and start to develop the relationships. So we double click and that is selected. So hopefully something useful will come up that we can use to solve the problem. And these examples will prove instructive. There's a lot of trigonometry in here. So two of these are problems that I used in my teaching, and one of them is one that my daughter brought home, and I thought, that's pretty nifty. I've never seen that before, so I'm going to use that. So yeah, it's all about trigonometry today. But the principle is the same, that you can just give names to some of the quantities in your problem and just develop the relationships, see where it leads. So this first one is that we've got a ship moving in the direction north 15.0 degrees west at a speed of 15 kilometers an hour. Well, of course, they often use knots in shipping and aviation because a knot is a nautical mile per hour, and a nautical mile is slightly different to a regular mile. It's 1 minute around a great circle. So we've got this boat with a speed of 22 kilometers per hour, and that is due east of the ship. And the boat wants to rendezvous with the ship. What direction does it travel in? So let's draw a diagram. And here, of course, we have due north. So for navigating purposes, and also in surveying, they use true north as 0 degrees. Then you go 90 degrees around to east. Then you go 90 degrees around to south, 90 degrees around. So south, of course, is 180, west is 270, and 360 is back to north again. So we know that this ship out here is going at 15 kilometers per hour, and this boat is going at 22 kilometers per hour, and hopefully they're going to intersect. Rendezvous might be the better word. We don't have a lot of information here. We don't in particular have the lengths of any sides because we don't know how long they're traveling, for what length of time they're traveling here, and we don't know the distance. We know some angles. So this is obviously a 90-degree angle here. This one here will be an extra 15 degrees because it's going north 15 degrees west. And that's all we know. So this is where we assign a name to some quantity, and I would suggest time t. You could pick the length of this side, but then you'd have to find the time t to find the length of this side anyway. So why not start with t? So we'll assume that the two craft meet after time t. And so the two sides will be of length 15t and 22t. So now our triangle looks like this, and I've given some letters. This is angle A, angle B, angle C. This is side A, opposite angle A. This is side B, opposite angle B. And this is side C, opposite angle C, as usual. So this angle A, of course, is 105 degrees because it's this 90 here plus this 15. And so we can use the law of sines to find this angle. And that will tell us what direction the ship has got to navigate in. Sine B on B is equal to sine A on A. And of course we could say B on sine B equals A on sine A and just invert them, but it's the same thing. So sine B is B sine A on A. I've got 15t on the bottom and 22t on the top, and that's a great relief because our t's cancel. I don't, in fact, need to know the time. Well, I just plug in the numbers, chuck them into my calculator, and I will get approximately 41.19 degrees. Now that literally is 41.19. It's not 41 degrees and 19 minutes. So we should sail at 90 minus 41.19, which is north 48.81 degrees west. Or, and let's put this in, or it will sail at 270 plus 41.19, which is, I'm about to cough, which is about 311.19 degrees. And I can't even see my degree symbol because it's behind my picture of myself. That, of course, would be degrees true. There we go. So that's the other way that we specify angles so far. Let's just make sure that I haven't made a hideous fool of myself with my mental arithmetic. Looks okay to me. Yeah, that's the other way of specifying it. So that, of course, would be 311.19 degrees clockwise from north. So, and that's our first example that worked out fairly simply. I do make a pretty good coffee, even if I do say so myself. Here's our second example. A triangle has angles of 60 degrees, 40 degrees, and 80 degrees. There's a point X, which is 5 centimeters from each vertex, and we want to find the length of each side. Well, that's just really bizarre. And this is the one that my daughter brought home. I hadn't seen this problem before, and I like it. We need to include information about lengths that we have, which is, of course, the distance from X to each vertex. And so I've drawn the lines from X to each vertex. I haven't put the length in because they're all 5. And we will need some angles. So let's make up some angles. So I've got theta and theta here, and of course, because these sides are both of length 5, this is an isosceles, they're both theta. These are both 5, so these are both phi, and again, both 5, so these are both alpha. So we've now got 3 triangles, each with 2 known lengths and no known angles whatsoever. So let's do something with our angles. This angle down here tells me that alpha plus theta is in fact 40. This one over here tells me that theta plus phi is 60. And this one over here tells me that alpha plus theta is 40. Sorry, phi plus alpha is equal to 80. 40 was down here. So alpha plus theta is 40. Theta plus phi is 60. Alpha plus phi is 80. That's a linear system of 3 equations in 3 unknowns. We should be able to solve that. We could use an augmented matrix, and first year uni students use those a lot, and they're really good, but it's a pretty simple system. We can manipulate the equations. Just let me finish my coffee. So phi is equal to 60 minus theta. I've gone for the second equation first for some reason. And then if I put that into the third equation, I've got 60 minus theta plus alpha is equal to 80. That's this one up here. And then if I come down here, I've got alpha is equal to 40 minus 60. And so if I put that into this equation as well, I get 60 minus theta plus 40 minus theta is equal to 80. And so if I rearrange that, I've got 60 plus 40 minus 80 is equal to 2 theta. Theta is, of course, 10. So, of course, this gives me that phi is equal to 50 and alpha is equal to 30. From here, we can use the law of cosines to find each side. I'm only going to do one. If you can do one, you can do the other two. So if we come back here and I'm looking at the triangle A to X to C, I've got the sides AX and CX of length 5, and I've got the angle A is 30, and the angle C is also 30, because they're both alpha, and the angle X here is 120. That's just by subtracting 2 30s from 180. Anyway, we whack that in and we get x squared is a squared plus c squared minus 2ac cos x. Chuck in the numbers, and on the right we'll get 75. And so x is actually, excuse me, the square root of that, which is 5 root 3. Now that is the exact answer. 5 root 3 is the exact answer. That's the one that mathematically we should give. If, of course, we're giving the solution to this problem to some engineer or surveyor or someone who's got to do something with it, they will want a decimal approximation. And in that case, we should provide that as well. But to say it's just 8.66 is technically incorrect, mathematically speaking. So make sure you give at least the exact solution. And if the decimal approximation is also needed, give that as well. And that way, if someone says, well, you know what, 3 significant figures here is not enough. Like, we're sending a spacecraft to the moon on the basis of this calculation, we need a bit more accuracy. They can just get their calculator out and say, well, 5 times root 3, and they can spout that off to 8 or 9 decimal places. So the exact answer is the most important. Okay, this is quite a different sort of example. Suppose we've got a pilot who wishes to fly on a bearing of, let's say, 50 degrees true, at a cruising speed of 130 knots. But there's a wind of 12 knots, and so this is the actual application where we are using knots and not being a nautical mile per hour. But if you want, you can think of that in terms of kilometers per hour. It doesn't actually matter. The method of solution will still be the same. That is blowing in the direction of 120 degrees true. Now, the pilot wants to aim the plane on some heading so that the aircraft will in fact travel along the bearing of 50 degrees. We want to find the heading and the ground speed. So the heading is the direction in which the plane actually flies. It's the direction in which the nose of the plane is pointed. The track is the direction in which the plane is actually flying. And the wind will push the plane slightly off course. And this was something I didn't really understand terribly well until I was sitting in my office at Mawson Lakes once, and I watched a plane coming into land, and of course this plane has got its wings out, and the plane was pointing in this direction, but the wind was so fierce that the plane was actually drifting across like that. And that day I got a really good understanding of the difference between the track and the heading. The heading is the direction the nose is pointing in. The track is the direction it's actually flying when you add the wind to the velocity of the plane. So what we've got here is, it's not my best diagram, I will tell you. This is the heading right here. The plane is flying in that direction, and that line there, that arc, actually indicates the angle h at which the plane is flying. This is true north, of course. And this is the direction the plane is flying in. This is the ground speed, which I've called A. Sorry, it's not the ground speed at all. It's the airspeed. It is the speed of the plane through the air. And that is 130 knots. Okay, now we've got this wind coming over here at 12 knots, and that is pushing the plane off course, and it's also affecting the speed over the ground. The speed over the ground is something slightly different. And so this angle here, from true north around to this side here, is in fact the track. And that is what we want to be 50 degrees. All right, we really, really want that to be 50 degrees. What we do know, what we can control, is this angle here, the H, the heading. The ground speed is set at 130, the wind speed is set at 12, and it's coming from over here. How do we find that? If I knew the heading, I could easily find the track. I'd find this angle here and add it, and I could find the ground speed. And I'm going to demonstrate that. And the reason is I'm going to use that number later on. So A, I want to demonstrate how we solve this problem, and B, I want that answer. So if we know the pilot is flying on a heading of 50 degrees, it's fairly simple. We just apply our regular trigonometric formulae, such as the law of sines and cosines. Our angle H is 50 degrees true. Now, we need to know this angle here. So we've got this side, we've got this side. We need to know this angle. Now, because the wind is blowing at an angle of 120 degrees true, that's 120 there. That makes this 60. And this angle here is in fact the same as this heading H, which for the moment is 50 degrees. All right. So our angle B is 50 plus 180 minus 120. That's 110 degrees. And so that's bigger than 90. Our ground speed is going to be larger than our airspeed. And so the wind is actually accelerating the plane slightly. So if we use the law of cosines, we've got G squared is equal to B squared. Where'd B come from? That should be G. My apologies. There we go. Well, G is B. So G squared is equal to B squared equals A squared plus C squared minus 2AC cos B. That's 130 squared, yada, yada. Just chuck all the numbers in. Put that into your calculator. And so, and of course, this should be approximately equals, really. But our G is approximately 134.6 kilometers per hour. And of course, when you're doing this for yourself, you should keep a large number of decimal places in your calculator. You might have to store that in memory somewhere or something. But don't write down 134.6 and then clear that from your calculator and then proceed calculating again. Keep the whole number there somewhere, even if you have to store it in memory. So this is the ground speed of the plane. We need to know the track, or the angle, or the course the plane is flying across the ground. And so that track, this is the track here, from due north around to this side, and that will be the heading plus this angle at A. And so we calculate sine A, that's A sine B on B, 12 sine 110 on 134.6, and I do the inverse sine of that. Again, don't write this down and clear your calculator and then put it in again and do the inverse sine. That's ridiculous. It's terrible, not just ridiculous. And so that is around about 4.8. And so the actual heading across the ground is about 54.8 degrees true. And there are, of course, limits on how accurately you can point the nose of the plane anyway. If you meet a pilot who says, well, actually, I could point the aircraft in the direction of 54.87321 degrees, feel free to challenge him on that, or her. Okay, so that was the solution technique. We don't know H, we're trying to find that, and we want the track, which is the heading plus the angle A, to be equal to 50 degrees. And it's really not that clear on how we proceed with this. So again, we're going to use our technique of just giving something a name, and we'll try and calculate it. We'll try and develop the relationships and see what we get. So the angle B is then H plus 180 minus 120, which is H plus 60. Now, the last time H was 50, that's where we got 110 from. Okay, so that's very simple, as if we know what H is. We don't yet. So we'll just leave it as H plus 60. Using the law of cosines, I'm going to cough again. Excuse me. Using the law of cosines, we get this. So I'm just using my law of cosines. I'm putting the numbers in, except that here, I've still got an H, not an actual number. But work with me on this. And so our B turns out to be the square root of this, yada, yada, yada. I've just put in all of those things. The sine of A is A sine B on B, and that is 12 cos H plus 60 on the square root of this. And so A is the inverse sine of this. Where on earth is this going? Still not clear on how to proceed, but we at least have a formula for the angle A. And it's highly nonlinear, you'll notice, very highly nonlinear. All right, now that we've got angle A, of course, we can find the track, which is given by H plus A. And so the track, T, is equal to H plus A, but A contains H. And so we can actually convert this into a fixed point iteration of the form H equals T minus A, which is 50, because that was our desired track, minus the sine of all these things, and there's H on this. So now there's H on the left and H on the right. Now, if you've done Newton's method in your maths courses, that is a formula, it's not a formula, it's a method that will find a solution to an equation of the form f of x equals 0, and the formula has got x on both sides. And so what you do is you start with an x value, a starting value, which we call the initial value on the left. We feed that into the equation here, we get a new number, that becomes our new x. So now we've got a new x value, we feed that into the equation on the right again, we crunch all the numbers, crunch them up really good, we get a new value, which we put into x again, and now we've got a third value for x, which is hopefully getting close to the answer, and we feed that in, we crunch all those numbers up, and so on. And we just repeat that. Now, sometimes that works and sometimes it doesn't. Those conditions are way beyond the scope of this, this chat. But the important thing is that we've got H on the left and we've got H on the right. And if we start with a suitable value of H and we just churn through a bunch of calculations, we might find that we get a series of increasingly accurate estimates of H that get closer and closer and closer to the true H. And at some stage, we're going to say, look, that's close enough. That's good enough. Particularly bearing in mind the limits on how accurately you can steer the plane anyway. And so, yeah, a very common method that works in a similar way is Newton's method. So we find a new estimate using the starting value of H. So we start with the value of H, we put that in here, and you say, aha, H is equal to this. Well, which is it? Is it the first one or the last one? It's actually both, just at different times. Starts off with the first value, we calculate a new value, that's our new H. We put that into the formula on the right-hand side, we calculate that, that's the next H, and so on. I'm going to use a table to try this out. All our angles have been converted to radians first. So we're not working with H plus 60, we're working with H plus 2 pi over 3. So pi over 3, 60 is pi over 3. G. And what I've done is, to start off with my initial estimate, I've actually subtracted the previous value of angle A, which was 4.8 degrees, converted to radians. So here's, excuse me, here's something I've copied out of Excel. This is our navigation inverse problem. Yeah, let's tell you what, let's throw in a page break. So what I've got is my desired track. That's the course that I want to be flying, 50 degrees. I've converted that to radians. My airspeed is 130 knots. My wind speed is 12. My wind direction is 120, and I've converted that to radians as well. So to convert from degrees to radians, you just multiply by pi and divide by 180. So here's my H0, H0, the first estimate of my track, and it's not a great one, but it's 45.2 degrees. In radians, that is this. So I just keep converting them to radians. And so here's my iterative process, and I've laid it out in a table. I could, if I wanted, just use this formula that doesn't reveal very much about the solution, because of course this is still a trigonometric process. And so what I've got is my headings, and this is the first one that I start with, and that I've just copied this. Now you'll notice that it's not to anywhere near as many decimal places. And I'm not entirely sure why. In fact, I have absolutely no idea why that one is only to 4 decimal places, and this one here is up to what, 2, 4, 6, 8, 9. Yeah. But Excel, of course, is still using all those decimal places. I can't see them, but Excel is still using them. So here's my angle B, which I have calculated by just using H plus pi over 3, not 60, because it's all in radians. The reason for that is that I suspect that there is a scaling advantage that you get if you use, and of course Excel uses radians anyway, so why not convert to radians? But I also suspect that you get a slight advantage by using radians, because you're dealing with smaller numbers. Anyway, so here's our ground speed G, and that should of course be a lowercase g. There's our ground speed, and that's just calculated using this formula here, using G instead of B, right? So I've just put the current H into that, and pi on 3, of course. That's that one there. Then I've calculated angle A using the law of sines. That, of course, is in radians. So here's my new heading, and I've just gone, it's the track, which is 0.872 minus this angle A. And so that's my new heading. I've converted that to degrees. And then this value here is just copied from this one. And you can see there's not a whole lot of change in these, but of course, to 8 or 9 decimal places, you would actually see some small changes. Maybe I should fix that up. But in any case, you can see that the course is actually converging very, very quickly. So we've probably done a little bit too much work. After one iteration, it's already at 45.03 degrees, and it stays at 45.02. I've really actually overdone it a little bit. But you should grab your calculator, make sure you can replicate the first row or 2 of these. And so eventually we get that the heading that we want to fly is 45.0239 degrees. Naturally, you cannot possibly steer the plane to this degree of precision. Okay. All right, I hope that that has been helpful to you. It's a very useful, I'm going to cough again. It's a very useful and helpful problem-solving technique. When you don't know how to proceed, just give some stuff some names, develop the relationships, see what you get. This one here is a little different from the others because there's no actual formula for the answer. Right? It's a process, and it's a numeric process. You have to keep churning through the numbers and you get successively better approximations to the true answer. And I could not tell you what the true answer is. What is the exact heading? I couldn't tell you that to say 20 decimal places. Whereas if I had to calculate 5 root 3, which we had earlier, to 20 decimal places, I could. I'd just use lots and lots of precision in the software. Whereas this one, I have no idea. And I would need to do a lot more calculation and a lot more work. But anyway, that is a very useful numerical technique. If you can write an equation with x on one side and something involving x on the other side, they might converge. If you start off with a suitable choice for x and you just churn through the numbers. So you may find that converges. Certainly did in this case. Okay, ladies and gentlemen, that's it for today, and I hope you find that useful. All right, carry on and keep doing maths.